All right, in this video, we're going to talk about section 4.5 dealing with absolute maxima and absolute minima. And in this video, we're going to be able to find the absolute extrema given the graph of a function and also find the absolute extrema of a function. And what I mean by absolute extrema, I'm talking about the absolute maximum and the absolute minimum. If you recall that f of c is a local maximum if f of x is less than or equal to f of c for x near c, and a local minimum if f of x is greater than or equal to c for x near c. In this section, we seek the largest and smallest values of f of x throughout the domain of the function f. Okay, so here's what absolute maxima and minima mean by definition. If f of x is greater than or equal to f of x for all the x in the domain of f, then f of c is called the absolute maximum of f. And also, if f of c is less than or equal to f of x for all the x in the domain of f, then f of c is called the absolute minimum of the function f. Now, the absolute maximum or absolute minimum is called an absolute extremum, okay, as I mentioned before. All right, now let's take a look at these illustrations here that you see on page 1. For this first graph that we have here, we have f of x is equal to x cubed divided by 3 minus 4x. In this case here, there is no absolute maximum or absolute minimum because notice, even though this may seem like the absolute maximum because it's the highest point here, this graph goes on indefinitely, okay? If we were to look at all the domain, which is from negative infinity to infinity, there's not going to be an absolute maximum because I can always find the highest y value on this graph. And the same for the absolute minimum. There is none because this graph goes indefinitely falling from the left, meaning there are negative f of x values that are greater than this lowest point on the graph. Okay? Now, there is one local maximum, which is at x is equal to negative 2. So that is a local maximum, but it's not an absolute maximum. And a local minimum is right here. It occurs at x equals 2. That's just a local minimum, but it's not the absolute minimum because I can come up with a value for f of x, an f of x value that's going to be less than this local minimum. All right, in part B, the absolute maximum, as you can see here, is, for this one, f of x equal to 4 minus x squared. Here's the absolute maximum at x equals 0 because this is the highest this y value will ever reach before it starts falling. And of course, there is no absolute minimum in this case as well. Now for this one, f of x equals to x to the 2/3 power. The absolute minimum only occurs at x equals 0. That's the lowest y value it would ever reach before it starts going in the other direction. And obviously, it goes indefinitely upward on both sides. There is no absolute maximum. All right. Now, in many applications, the domain of a function is restricted because of practical or physical considerations. Prices and quantities cannot be negative. Factories cannot produce arbitrarily large number of goods. If the domain is restricted for some closed interval, as is often the case, then this theorem, theorem number 1, applies. And this is theorem number 1 dealing with the extreme value theorem. And that's a function f that is continuous on a closed interval, which is of course a comma b, has both an absolute maximum and an absolute minimum on that interval. So here, when you have a closed interval, that means there is restriction there. That means we can find both the absolute maximum and the absolute minimum on that interval. So like in these illustrations here for the absolute extrema, if I can get to the paper, okay. So in this case here, you'll see what those absolute maximums and absolute minimums will be for each graph. And this is for the function f of x equals to x cubed minus 21x squared plus 135x minus 170. And this is for various closed intervals. This first graph is for the interval 212. So if you look at where a is 2 and b is 12, you can see that the absolute minimum is right here. It's 24. It occurs when x is equal to 2 or when a is equal to 2. And here the absolute maximum is 154. It occurs when b is equal to 12. Now, if we restrict it a little bit more from 4 to 10, in this case, for that same function f of x, this time, here's 4, and I might as well use this red marker. Here's 4, and the other one is 10. Okay, here's 10. You're going to see that right here is your absolute maximum. It occurs when x is equal to 5. The absolute maximum is 105 within that interval 410. It occurs when x is equal to 5. And then here, your absolute minimum is right there. It's 73. It occurs when x is equal to 9. All right. Now for the absolute maximum here for this graph, when the interval is now from 4 to 8. So here, 4 is right here, and 8 is right here. Here, your absolute maximum is still going to be 105, and it occurs when x is equal to 5. Now, we restrict it from 4 to 8, so now this will become your absolute minimum, which is in this case going to be 78. It occurs when x is equal to 8. And then the last one on the right-hand side, we're restricting it from 3 to 11. So here's 3, and here's 11. You can see where your absolute minimum is. You have 2 of them. They occur at x equals 3 and at x is equal to 9. Your absolute minimum is 73. Now your absolute maximum is still going to be 105. It occurs at x equals 5, but not only that, it's also occurring when x is equal to 11. Okay. All right, so that's how we find the absolute maximum and absolute minimum from a graph that's given to us. So here's some examples of this. Starting with example 1. For the graph of y equals f of x shown here, we're going to find the absolute minimum and the absolute maximum over the interval 1 to 11. So in this case here, we're looking at the x-axis here. Here's 1 right here. And that's 12, so to the left of that is 11. So here's 11 here. So within this interval, we're going to find the absolute maximum and absolute minimum. So I go ahead and write down absolute maximum and absolute minimum. Starting with the absolute maximum. Within this interval, where's the highest y value at? It's going to be right here. All right, so here's that highest y value right here, and it's going to be at, in this case, 13. So the absolute maximum is 13, and it occurs at what x value? In this case, it's going to be this x value right here. So it's going to be, this is 1, this is going to be 2, 3, and 4. So at x equals 4, that will be your absolute maximum at 13. Now for the absolute minimum. Here's the lowest, excuse me, here's the lowest y value it would ever reach before it, I need to make a correction about the absolute maximum. Okay, it's within the interval 1 to 11. So in other words, here's your absolute maximum up here. Here's 11, is right here. Okay, because if I cover just the part after 11, which is right here, you're going to see this is the highest y value it would reach. So that highest y value will have to be, in this case, 18. So the absolute maximum is 18. And it occurs at x equals 11. Okay? All right, that's the mistake right there. So you have to look at the interval first to find your maximum, absolute maximum. Now for the absolute minimum. That's the smallest y value it would ever reach. Well, going from 1 to 11, if I cover this part up, anything to the left of 1, we can see our lowest y value will be about right here. And it occurs at x equals 1. It'll be about right here. So here, that absolute minimum will be 3. And it occurs at x is equal to 1. Okay, so I know it's a little bit hard to see here, but here, that graph at 1 is going to be 3. So that's the absolute minimum. Right, here's another example. Let's say we had this graph and we want to find the absolute maximum and the absolute minimum over the interval 1 to 12. So this is 1 right here. That's this interval, 8, 9, 10, 11, 12. So we're only looking at this interval from 1 to 12 to find the absolute maximum. So I'll be looking at points from here up to here. And if I cover the right side of this graph, you're going to see where the absolute maximum will be. And not only that, I'm going to cover everything to the left of 1, which is right here. I'm going to cover that up. So here, the absolute maximum on that interval will be right up here. That's this point here. Now let's find out what that y value is going to be. If you look at it, the y value is going to be 9. So your absolute maximum is going to be 9. And it occurs at what x value? In this case, if that's 1, this is going to be 2, 3, 4, 5. It occurs at x is equal to 5. So the absolute maximum is 9. It occurs at x is equal to 5. Now let's go ahead and find the absolute minimum. The absolute minimum, that's going to be the lowest y value on the interval from 1 to 12. Well, here's the lowest y value right here. Okay. Actually, it's going to be right here. Okay. Because here's the original graph here. So that y value is going to be crossing the x-axis at 1. So the absolute minimum is 0. And it occurs at x is equal to 1. Okay. All right, next example. Here we're going to again find the absolute minimum and absolute maximum over the interval from 1 to 16. Okay. So here's 1. To the left of 17 is 16. So that's the interval that we are going to be looking at in this case. So I'm going to cover up everything to the left of 1, everything to the right of 16, and focus on that graph within this interval. Let's first find the absolute maximum. Well, the absolute maximum occurs right up here. That's this point right here. And the absolute minimum, it occurs here and here. So we got 2 different places for our absolute minimum. All right, so let's go ahead and write down what that absolute maximum is. The absolute maximum, that's going to be the y value, which is in this case 12, occurs at x is equal to, in this case, 16. Absolute minimum, and here that y value there will be at 5, because this is 6, in between 6 and 7 is 6.5. So this is going to be the absolute minimum, which will be the y value of 5. It occurs at 2 different x values, as I mentioned. One of them will be at x is equal to 3. I'll take that back. At x equals 2. No, it's at x equals 3. And the other one will be at x is equal to 11. And here's one more of these. By looking at the graph, we're going to find the absolute maximum and the absolute minimum over the interval from 0 to 10. So this will be from 0, which is here, and 10, which is here. So this will be probably our lowest point from 0 to 10, and the highest point from 0 to 10. So let's start with the absolute maximum. Absolute maximum is the highest point here. That y value there will be 17. And it occurs at x is equal to, in this case, 10. Then for the absolute minimum, here, this is the lowest y value it would ever reach. On that interval, it will be at absolute minimum will be the y value at 1. It occurs at x is equal to 0. Because as you can see, that graph crosses the x-axis at 1 when x is equal to 0. Okay? All right, so that's how we find the maximum and the minimum values over an interval when you're given a graph. All right, so now let's look at the next theorem where we're going to actually locate absolute extrema. And here's the procedure for doing that. But before that, let me tell you what theorem 2 states. Absolute extrema, if they exist, must occur at critical numbers or at endpoints. Absolute extrema must occur at critical numbers or at endpoints. And here's the procedure for doing that. So here we're going to find an absolute extrema on a closed interval. Number one, you want to check to make certain that the function f is continuous over the closed interval AB. And then number two, find your critical numbers in the interval a comma b, and that's the open interval AB in this case, because it has parentheses. Closed interval has brackets. Number three, evaluate f at the endpoints a and b and at the critical numbers that were found in step number 2. Now, the absolute maximum of the function f on the closed interval AB will be the largest of the values found in step 3, and then your absolute minimum of the function f on the closed interval AB will be the smallest of the values found in step 3. Okay. So now we're going to apply that theorem to these examples. And that's this. Let's say we want to find the absolute maximum and minimum values of the function over the interval and indicate the values or the x values at which they occur. So here we got the function f of x is equal to x squared minus 10x minus 4. And the indicated interval will be from the closed interval 1, 8. Okay, so here is our function f of x equals to x squared minus 10x minus 4. Now we want to find out if that function is continuous on that closed interval 1, 8. Well, by looking at this, it is a polynomial function. So that means here, any polynomial function where you give an x value, you're always going to get an f of x value for it. So it is continuous. This function is continuous on, I'll say the interval negative infinity to infinity. Okay, because if it's continuous on that interval, negative infinity to infinity, it must be continuous on the closed interval, 1 comma 8. Now, let's go ahead and find what our critical numbers are going to be. And the way you do that is to take the first derivative of this function. So f prime of x would be 2x minus 10. And then next we're going to set the function f prime of x equal to 0 at our critical numbers. So that means we take 2x minus 10, set that equal to 0, and then solve for x. So if I add 10 to both sides, that will mean I'll have 2x is equal to 10, and then divide both sides by 2. That will mean x equals 5. That x equals 5 is my critical number. All right, so now the next step, step number 3, would be to evaluate that function at the endpoints, a and b, and at the critical numbers found in step number 2. So that means I need to find out what f of 1 is, since this is my interval that I'm using, 1 comma 8. Also, I need to evaluate f of 8 and evaluate f of 5, which is my critical number. Now, using the original function that I have, I'm going to substitute each and every x with these values here, starting with f of 1. I'm going to have 1 squared is 10 times 1 minus 4. And in this case here, I'm going to have 1 squared, which will be 1. It's 10 times 1, which is 10, minus 4. I'm sorry. All right, in this case here, 1 minus 10 is negative 9. Negative 9 minus 4 would be 13. So f of 1 would be negative 13. All right, now for f of 8. To evaluate f of 8, I just substitute each x in the f of x function with 8. So it would be 8 squared minus 10 times x, which is 8, minus 4. So here 8 squared, or 8 times 8, is 64, minus 10 times 8, which is 80, minus 4. And I'll go ahead and do 64 minus 80 minus 4. That will end up being negative 20. Okay. And then for f of 5, which is my critical number, replace the x in f of x with the 5. So it'll be 5 squared minus 10 times 5 minus 4. So 5 squared will be 25 minus 10 times 5, which is 50, minus 4. So here I'm going to do 25 minus 50 minus 4, and that would give me negative 29. Okay? So now I need to, in this case, find out what the absolute maximum is. That's going to be the larger of the values found from step 3. The absolute minimum would be the smallest of the values. So the largest here, and that's going to be the number that's closest to 0, will have to be this one, negative 13. That's closest to 0, so that's going to be the largest. That will represent the absolute maximum. So my absolute maximum is 13. It occurs at x is equal to 1. Okay? And sometimes they write as an ordered pair 1 comma 13 as your absolute maximum. And then for the absolute minimum, that's the smallest of all the values. The one that's furthest away from 0 is negative 29. So your absolute minimum is negative 29. not absolute maximum. We already know what that is. So absolute minimum. Here you go. Absolute minimum is 29. It occurs at the x value of 5. Sometimes they write 5, negative 29, as your absolute minimum. Okay? So that's how we find the absolute maximum and the absolute minimum using that procedure that I gave you. Here's another example. Let's say we had this. We got f of x equal to x cubed minus 9x squared plus 15x plus 5. And we're going to find the absolute maximum and minimum if either exists for the function on each of the following intervals. In part A, you got the interval negative 2, 8. Part B, the interval negative 2, 5. And part C, the interval 2, 8. Just 2, 8. We'll start with first, finding out where it's continuous. Again, you have a polynomial function, so that tells me that this function is continuous everywhere from negative infinity to infinity. That will mean that it's going to be continuous on all three of these intervals that are given in parts A, B, and C. Now let's find the derivative to find out what our critical numbers are going to be. So here, f prime of x would be this. The derivative of 3x squared would be, the derivative of x cubed, I gave that away, that's 3x squared, minus the derivative of 9x squared, that would be 18x, plus the derivative of 15x would be 15. The derivative of 5 is 0. So I have f prime of x equaling to 3x squared minus 18x plus 15. Now we're going to set f prime of x to be equal to 0 to identify our critical numbers. So that means 3x squared minus 18x plus 15 equal 0. Now, let's solve for x. Let's do some factoring here because I know 3x squared, 8 minus 18x, and 15 have a common factor of 3. So if I factor out a 3, that means 3x squared divided by 3, that'd be x squared, minus 18x divided by 3 will be 6x, plus 15 divided by 3 will be 5. So I got 3 times x squared minus 6x plus 15 equal to 0. And then the next step would be to factor x squared minus 6x plus 5 completely into two binomials. So I'm going to bring down the 3. Squared breaks up as x and x. The middle term is a minus and the last term is a plus, so they both have to be minus. Factors of 5, that gives me a sum of 6. X as a middle term would be 5 and 1. So I have 3 times the quantity x minus 5 times the quantity x minus 1 is equal to 0. So here I'm going to set each factor equal to 0. So this means 3 is equal to 0. X minus 5 is equal to 0. X minus 1 is equal to 0. For 3 equal to 0, I can cross that out. For x minus 5 is equal to 0, if I add 5, I'm going to get x is equal to 5. And then for x minus 1 is equal to 0, if I add 1, so here I got x is equal to 1. So as you can see here, my two critical numbers are x equals 5 and x is equal to 1. That will be used in parts A, B, and C when I find the absolute maximum and minimum. All right, so starting with part A, I have the interval negative 2 and 8. So now What I'm going to do here is evaluate the function at the endpoints and those critical numbers. My endpoints are -2 and 8, so I'm going to be evaluating f of -2 and f of +8. And also my critical numbers, I'm going to evaluate f of 5 and f of 1. So here I'm going to substitute each x with those values here in this f of x function. So in this case here, f of -2 means this. I'm going to have -2, and that's cube, minus 9 times x, which is -2, and that's squared, plus 15 times -2 plus 5. And I'm going to do all of this in the calculator to save time, because this will be a lot. All right, so left parentheses, -2, close parentheses. To cube it, I'm going to use the hat key and type in the exponent of 3, and then use my right arrow key to get out of it. Minus 9, and then left parentheses, -2, close parentheses, and then square it. Plus 15, left parentheses, -2, close parentheses, plus 5, and then hit enter. That would be -69. And now for f of 8. Here I'm going to replace each x with 8, so this will be 8 cube minus 9 times x, which is 8, plus 15 times x, which is 8, and this 8 needs to be squared, plus 5, plus 5. So here I'm going to have 8, and then cube minus 9 times 8, and that's going to be squared, plus 15 times 8, plus 5. I end up with 61. So for f of 8, that would be 61. 5, I'm going to replace each x with a 5. So let me move this over. So this will be 5, and that's going to be cube. 5 cubed minus 9 times 5, and that's going to be squared. Plus 15 times x, which is 5, and then plus 5. So in this case here, 5, and then that's cube minus 9 times 5, that's squared, plus 15 times 5, plus 5. He'll come up with -20. And then for f of 1, that's just going to be 1 cube minus 9 times 1, and that's squared, plus 15 times 1, plus 5. So here I'm going to have a 1, and then that's cube minus 9 times 1, that's squared, plus 15 times 1, plus 5. End up getting 12. So from here, I can identify the absolute maximum and the absolute minimum. The absolute maximum is the highest of these numbers here, and the highest here is 61. So your absolute maximum is 61. It occurs at x is equal to 8, because at x equals 8, our absolute maximum was 61. And sometimes they use the order pair 8, 61. And now your absolute minimum. That's the smallest of these values here. In this case, it's going to be negative 69. So your absolute minimum is negative 69. It occurs at x is equal to, in this case, negative 2. And sometimes they like to use the order pair negative 2, negative 69 to indicate the absolute minimum. Okay, so that's part A, just identifying the absolute minimum and maximum for the interval negative 2, 8. Part B is from negative 2 to 5. Okay, now, this is quite easy because notice here, we can't use x equals 1. Oh, yes, we can. We can use x equals 1, and we can also use x is equal to 5. Okay. Now, keep in mind the 5 has already been evaluated here. So, f of negative 2, we already know. That's negative 69. F of 5 is what we already know as well. Here's f of 5 right here. That's negative 20. F of 1, we already know that. From here, that's going to be 12. So now we can use this to identify the absolute maximum and absolute minimum. So the absolute maximum is going to be the larger of those values here. And in this case, the highest is 12. So the absolute maximum is 12. It occurs at x is equal to 1. And again, the order pair 112 might sometimes be used to identify the absolute maximum. And the absolute minimum that's the smaller of these three values here. That's negative 69. It occurs at x is equal to negative 2. And sometimes they use the ordered pair to identify an absolute minimum as well. Okay, and it depends upon the homework. All right, so that's part B. Part C will be the interval 2, 8. Okay. Now, since our interval is from 2 to 8, we're not going to be using x equals 1 as our critical number because that's outside the interval 2, 8. Okay? So all we need to do there is just evaluate f of 2 and f of 5 and also f of 8. Because we have our endpoints 2 to 8 and then 5 is within the interval 2, 8. We're not using x equals 1 because that's outside the interval. Now for f of 2, we need to go ahead and substitute each x in the original function with 2. So it would be 2 cubed minus 9 times 2 squared plus 15 times 2 plus 5. Okay, because I believe that's the only x value that we haven't evaluated. So here this will be 2, and then that's going to be cubed minus 9 times 2, and that's squared, plus 15 times 2, plus 5. And here I get 7. So f of 2 will be 7. Now for the f of 5, I believe we've already figured that out. F of 5 is right up here. That's negative 20. And also f of 8. Yeah, here's f of 8. That value was 61. All right, so let's find the absolute maximum. That's the larger of those three values here. Your absolute maximum will have to be the 61. And it occurs at x is equal to 8. And then your absolute minimum that's the smallest of these three, which is negative 20. And it occurs when x is equal to 5. So 5, negative 20 would be the order of pair for the absolute minimum if they ask for it. Okay? So that's how we find the absolute maximum and the minimum for the function at those indicated intervals. Okay? All right, next we'll look at is the second derivative test for local extrema. The second derivative test for local extrema. And here we're going to let C be a critical number of f of x such that f prime of x is equal to 0. If the second derivative, f double prime of x is greater than 0, then f of c has a local minimum. If f double prime of c is less than 0, then f of c has a local maximum. And here's the table for that. F prime of c is 0, but f double prime of c is positive. That means that the graph of that function will be concave upward, meaning you're going to have a local minimum. And that's just an illustration of that. Concave upward means you're going to have a local minimum. But if f prime of c is 0 and f double prime of c is negative, that means your graph will be concave downward, meaning you're going to have a local maximum. And an illustration of that would be something like this. You can see it's concave downward, and that means you're going to have a local maximum there. But if f prime of c is 0 and f double prime of c is 0, then the test fails. Okay. So in this example, number 7, we're going to find the absolute maximum and minimum if either exists for f of x is equal to x squared minus 8x plus 2. So here we got f of x is equal to x squared minus 8x plus 2. Let's first find its first derivative. So f prime of x is this. The derivative of x squared is 2x, minus the derivative of 8x will be x, and the derivative of, 8, the derivative of 2 is 0. So f prime of x is going to be 2x minus 8. Now let's find that critical number by setting f prime of x to be equal to 0. So here we're going to have 2x minus 8 equal to 0. And solve for x. So if I add 8 to both sides, that means I have 2x is equal to 8. Divide by 2, x is equal to 4. So my critical number will be at x is equal to 4. Okay. So now let's substitute that x in the f of x function with 4. So f of 4 is going to be this. 4 squared minus 8 times 4 plus 2. 4 squared is 16 minus 8 times 4 will be 32 plus 2. 16 plus 32 will be negative 16. Negative 16 plus 2 will be negative 14. So f of 4 will be negative 14. All right? Now, we know what f prime of x is. Let's find out what f double prime of x is going to be. This is where we're going to use that second derivative test. Well, if f prime of x is 2x minus 8, then the derivative of that would be f double prime of x. The derivative of 2x would just be 2. And the derivative of 8 will be 0. So f prime of x is equal to 2. And as you can see here, f double prime of x is equal to 2. That means we come up with a positive number. Because we can take x equals 4 and find out what that is. F double prime of 4 is still going to be 2. So it's a positive number. So that means from this second derivative test, f prime of c is 0, but f double prime of c came out to be positive. It's going to be concave upwards, so that means f of c has a local minimum. As a local minimum. But since there's only one number, one x value for that, that means it has a absolute minimum. Absolute minimum. And that absolute minimum will be right here, 14, negative 14. It occurs at x is equal to 4, or it could be the ordered pair of 4 and negative 14. But here in this case, it will not have an absolute maximum. So for absolute maximum, we'll just say none. Or select the choice, there is no absolute maximum. Question, well, if you have questions about this, please feel free to reach out to me by email. Okay, example 8 looks like this. We're going to find the absolute extremum, if there is one, for the following function, f of x equals to 2x to the 4th minus 9. So I'll write the function f of x is equal to 2x to the 4th minus 9. Let's find that first derivative. So f prime of x is this. Bring the 4 down, multiply it by 2, will be 8. Copy the x over to the 1 less power. It'll be 8x cubed. The derivative of minus 9 will be 0. Now let's set f prime of x to be equal to 0. So that means 8x cubed is equal to 0. Divide both sides by 8, you'll get x cubed is equal to 0. And if I take the cube root on both sides, that would mean x has to be equal to 0. Okay. And also we're going to find f double prime of x. Well, if f prime of x is 8x cubed, then f double prime of x will have to be 24x squared. Bring the 3 down, multiply by 8, you'll get 24. Copy the x down to the 1 less power. Okay? So I'll set that 24x squared, which is f double prime of x, that would be equal to 0. If I divide both sides by 24, you'll get x squared is equal to 0. And that will mean, if I take the square root on both sides, and I'm not going to need the plus or minus symbol, so x will have to be equal to 0 as well. So as you can see here, the test fails, so that means I'll have to use that first derivative test, okay? Because notice that f prime of c is 0 and f double prime of c is 0. The test does not apply. I have to use that first derivative test. And in this case, I have to use that sign chart to determine whether it's increasing or decreasing on the interval. So the critical number is going to be x equals 0. So here's 0. And this breaks up that number line into two intervals. One would be from negative infinity to 0. The other one will be from 0 to infinity. All right, so now we pick test values here. So from negative infinity to 0, a good test value would be x equal negative 1. And I'm using f prime of x, which is equal to 8x cubed. So it'll be f prime of, replace the x with negative 1, that will be 8 times negative 1, and that's cube. Cube of negative is going to be a negative, so negative 1 cubed would be negative 1 times the 8 in front would be negative 8. And it is negative. So that means on the interval from negative infinity to 0, the graph of the function will be decreasing. And then from 0 to infinity, I will test, let's say x is equal to positive 1. So f prime of positive 1 will be 8 times 1 cubed. 1 cubed will be 1. 1 times 8 will be 8. Here, 8 is a positive number for f prime of 1. So that means on the interval from 0 to infinity, the graph of that function will be increasing. So you can see it's changing from decreasing to increasing. So if it's decreasing, and then after 0, it increases. That tells me at 0, I have a absolute minimum, because I only have one critical number. That has to be the absolute minimum. So here, the absolute minimum is at x is equal to 0. But let's find out what that absolute minimum is by replacing the x in the original function f of x with 0. So f of 0 will be 2 times 0 raised to the 4th minus 9. Well, in this case here, if 0 to the 4th is going to be 0 times 2, which is 0, 0 minus 9, that's negative 9. So my absolute minimum would be negative 9. It occurs at x is equal to 0. So if it was as an ordered pair, it would be 0, negative 9. And in this case, there are no absolute maximum. So for absolute maximum, we'll just say none. Okay. All right, let's look at the next example here. Find the absolute maximum and minimum if either exists for f of x is equal to 12x cubed minus 3x to the 4th. All right, so first of all, we need to find out what that first derivative is so we can identify our critical numbers. In this case, if I take f prime of x, the derivative of 12x cubed would be 36x squared minus the derivative of 3x to the 4th would be 12x cubed. So here, we'll set f prime of x to be equal to 0. So that means I have 36x squared minus 12x cubed equal to 0. All right, so now let's factor the left-hand side. 36 and 12 have a common factor of 12, so I know I can factor out the 12. X squared, x cubed, there's an x that's in both. I'll take the one with the smallest exponent as the common factor. It will have to be x squared. So 12x squared will be the common factor. Do 36x squared divided by 12x squared, that would be just 3 minus 12 divided by 12, that's 1. But if I factor x squared out of the x cubed, I'll be left with an x. So I have 12x squared times 3 minus x will be equal to 0. And then we set each factor to be equal to 0. So this means I'm going to have 12x squared equal to 0. 3 minus x is equal to 0. Well, for 12x squared equal to 0, that would mean x squared is equal to 0. And if I take the square root on both sides, that would mean x is equal to 0. Now for the 3 minus x is equal to 0, I'm going to do this. I'm going to add x to both sides. That way you're going to see that x is equal to 3. So those are my critical numbers here. X equals 0 and x is equal to 3. And now we're going to find out what f double prime of x is going to be. So this right here represents f of x. So here's f double prime of x. If I take the derivative of 36x squared, I'm going to get 72x minus the derivative of 12x cubed would be 36x squared. And now I'm going to substitute each x in the f double prime of x function with 0 and then with 3. We'll start with f double prime of x, or f double prime of 0. Substituting each x with 0, you'll get 72 times 0 minus 36 times 0, and that's squared. Well, that's going to be 0. 0 squared is 0 times 36 is 0, so 0 minus 0 is 0. So here, f prime was 0, f double prime was 0, so that means that the second derivative test fails. But let's find out what's happening at x equals 3 when I replace the x in f double in the second derivative function with 3. Here I'm going to have 72 times 3 minus 36 times 3, and that's going to be squared. Let's see, 72 times 3 will be, well, I'll go ahead and use some calculator to save time. I'm going to do 72 times 3 minus 36 times 3, and then that's going to be squared, and then equal, in this case, negative 108. So in this case here, my f prime was 0, f double prime came out to be negative, so based on that table here, 0 came out negative, local maximum. Okay, and it's going to be concave down. So that tells me I have a local maximum. X equals 3. And I'm only going to have like one local maximum, so that means this will have to be the absolute maximum at x is equal to 3. Not local maximum, absolute maximum at x equals 3. Let's find out what that absolute maximum is at x is equal to 3 by just replacing the x in the original function with 3. So f of 3 will be this, 12 times x, which is 3, and that's cube, minus 3 times x, which is 3, and that's going to be to the 4th power. And I will type this in the calculator. Let's do 12, and then left parentheses 3, close parentheses, hat key, and then the 3 for your exponent. Right arrow to get out of it, minus 3, left parentheses, type in the 3 closer, parentheses, hat key again, and then hit the number 4 for your exponent. It ends up being 81. So your absolute maximum is 81. It occurs when x is equal to 3. I'll write it again. Absolute maximum is equal to 81. It occurs at x is equal to 3. And sometimes they write the ordered pair 3, 81. And then for your absolute minimum, there is none. So in this case here, there is no absolute minimum. But there is an absolute maximum, and that's at 81. It occurs when x is equal to 3. And finally, on the last page is going to be the second derivative test for absolute extrema on an interval that's given to you. So here you're going to let x be continuous on an interval I from a to b with only one critical number, c, in the interval a comma b. That's the open interval, by the way, as you can see. If f prime of c is equal to 0 and f double prime of c is greater than 0, then f of c is the absolute minimum of f on that interval I. But if f prime of c is equal to 0 and f double prime of c is less than 0, then f of c is your absolute maximum of the function f on the interval I. All right, so now let's look at this example here. We're going to find the absolute minimum value on 0 to infinity for f of x equal to x squared minus 4x plus 1. So here f of x is equal to x squared minus 4x plus 1. Let's find its derivative here. So f prime of x would be the derivative of x squared is 2x. The derivative of minus 4x will be minus 4. The derivative of 1 is 0. So f prime of x is 2x minus 4. And then we're going to set f prime of x to be equal to 0. So that means we'll have 2x minus 4 is equal to 0. Solving for x, if you add 4, that would mean 2x is equal to 4. Divide both sides by 2. X is equal to 2. So now let's go ahead and find our absolute minimum by using that procedure of evaluating the endpoints A and B and the critical numbers. Okay, so now my critical number is x equals 2, so we'll evaluate f of 2. My endpoint is 0, so that's f of 0. Now my other endpoint is infinity. So the way we're going to have to do that is use this. We have to take the limit as x approaches infinity of the function f of x. So anytime you got infinity, either positive or negative, you'll have to take the limit as x approaches infinity to see what's going on. All right, so f of 2, using f of x equal x squared minus 4x plus 1, I just substitute each x with 2. This will be 2 squared minus 4 times x, which is 2, plus 1. Well, 2 squared will be 4, minus 4 times 2, which is 8, plus 1. 4 minus 8 would be negative 4. Negative 4 plus 1 would be negative 3. So f of 2 would give me negative 3. And then for x equals 0, this will be 0 squared minus 4 times 0 minus 4 times 0 plus 1. Well, 0 squared is 0, minus 4 times 0 is 0, plus 1. That ends up being 1. Now for the limit as x approaches infinity of the function f of x. That would mean I'm taking the limit as x approaches infinity of the x squared minus 4x plus 1. And by looking at this, the leading term is x squared. As I let x get bigger and bigger and bigger, then x squared would get closer and closer to, and it's just going to go off to infinity without end. Okay? So now, what would be our absolute minimum is what they're looking for. That's the lowest. Has to be 3, negative 3. So that means your absolute minimum is negative 3. And it occurs at x is equal to 2. And sometimes they use the ordered pair 2, negative 3. Okay? So that's how we find the absolute minimum on an interval that's given to us. All right, so that does conclude this video on section 4.5 dealing with absolute maxima and absolute minima. Feel free to reach out to me if you have any questions about any of the examples that were presented in this video or any questions about the homework in my math lab.